Hello and welcome back to Calculus 3 section on tangent planes, linear approximation and differentials. We're going to make this two-part, so part one today on tangent planes and then linear approximation differentials. We'll do that next time. So we have the idea of a surface, and that surface is going to have, instead of a tangent line, for which you have to have a direction to find, right? We're going to have a tangent plane. So in Calculus 1, we had a two-dimensional function, and we had the tangent line. Now we're going to have a tangent plane. What are you going to... Did you ever wonder why the graduation hats look the way they are? It's just a tangent plane application. That's all it is, right? It's, yeah. So that's all it is. So we have that idea. If the surface is smooth, then there is going to be a tangent plane. So do you have the tangent plane at the tip of a cone? The answer is no, because tip of the cone is not differentiable, so you can't have the tangent plane there. Just like you can't have a tangent line at the tip of the absolute value of x, because it's a spike there, right? And it's not differentiable. So in order for us to have the tangent plane, we have to have a smooth surface, differentiable surface. And then we also know that the tangent plane would measure, right, because it's slanted, it would measure the change at that point. So obviously, if there is a change, there is a derivative involved. So we're going to deal with that. So equation of the tangent plane. First, I'm going to write stuff, and then we're going to put the definition. So please recall that the plane in our Calc 3 was given by equation A, x minus x0 plus b, y minus y0 plus c with the z minus z0 equals to 0, where the normal vector n was given by this A, B, C, and the point P0 at which the plane was fixed was given by x0, y0, z0, right? So those were the specs of the plane from before. Now let's go with whatever this color is. Now we are looking at the tangent plane, and we are going to have, instead of A, B, and C, we are going to have derivatives in there. So it's going to be tangent plane at, this is now the little bit of an issue because the notation is changing. It's changing a lot, so please be careful. What used to be used ABC, what used to be called ABC, was in the vector, normal vector n, but now ABC is the point at which the tangent plane is happening. So that's a big jump between these three, right? So technically now ABC is your P0. That's what it is. It's changing. And we are going to have, instead of A, we're going to have fx computed at ABC, and then x minus a. So x0 is replaced by lowercase a, which is now x coordinate of the point, plus partial derivative in respect to y, computed at ABC, and then y minus b plus partial derivative of z computed at ABC times z minus c is equal to 0. So as you can see, notation has changed, and now your old ABC normal vector is now the vector of partial derivatives, and your point that used to be x0, y0, z0 is now called ABC. So notation has changed. This is a lot of writing. It's a lot of writing. So there is an easier way to note this, and we'll see the vector formula. All right, so that's just me comparing the new formula to the old formula and how the notation has changed. Now we can go and take a look at the actual definition for this using this new notation. So definition says let f be differentiable at point p0. So let f be differentiable at point p0, and p0 is given as ABC. So there's that change. With delta f, del f, being different than 0. So that's another, well, at ABC. So the plane tangent to the surface fxyz equal to 0 at p0, called the tangent plane, is the plane passing through P0, orthogonal to del f at ABC. And then the equation is fx ABC x minus a, the same equation we had up there, plus fy ABC times y minus b plus fz ABC times z minus c equal to 0. This is a lot of writing for something that we can simply express as, let's go with blue, del f at ABC dotted with p minus p0, right, which is a vector. Equals 0. That's the dot product. So, hold on, not p minus p0, sorry. Vector p0p, there we go. So we know that the gradient is fx, fy, fz. We know that the point p0 is ABC, And we know that the point P is x, y, z, because that's any point. So that's dotted by, and now you have your x minus a, y minus b, and z minus c. And because we want them to be orthogonal, its dot product is 0, and when you do the dot product you get the exploded version up there. So as an example of this, you might have, let's say you have some kind of elliptical paraboloid, so some kind of ellipsoid. Let's go with ellipsoid. So let's say your ellipsoid is x squared over 4 plus y squared over 16 plus z squared over 9 is equal to 1. So this is ellipsoid, and now let's say you want to have a point 1, 1, and then we actually have to compute now the third value. So I'm just going to do this on a side. If I use 1, 1, there will be 1/4 plus 1 over 16, 1 minus that, everything times 9, and then the square root, right? Because I need to move these two this way, and then multiply by 9, and then take square root to calculate z. Okay, cool. So this is what we have. The square root of 9 is 3, so kick that out. Over here you have a common denominator of 16. There will be a 16 minus 4 minus 1. So 3 square root of, well, quarter comes out. 16 minus 4 is 12 minus 1 square root of 11. So this is 3 root 11 over 4. Because I picked anything, obviously it's not going to be nice. Alright, great. That was just me computing the value z. So this would be a problem. If I'm creating a problem, I'm giving you a formula, and when I give you a formula, I am also giving you the point at which this works. So all I did is I plugged in, I picked any x and a y, I could pick any other value, doesn't matter. So now what happens? Well, we have fx first, so fx would be just 2x over 4, which is x over 2. Then I need fy, which would be 2y over 16, which is y over 8. And finally, I have fz, which would be 2z over 9, which is just 2z over 9. That's that. So now, fx computed at 1, 1, 3 root, who picked these numbers, is going to be just 1/2. Fy computed at 1, 1, 3 root 11 over 4 is going to be 1 over 8. And fz computed at this point is going to be 2 times 3 root 11 over 4, everything over 9. So that is 2, 18, 3, 6. So root 11 over 6, if I did this correct. Let's see, 3 and 9 will cancel. This is the main division line here. So 3 and 9 will cancel, give me a 3, and then, yes, root 11 over 6. So what is the tangent plane? Tangent plane is going to be fx, so that's 1/2 x minus 1, plus fy is 1 over 8, y minus 1, and then plus root 11 over 6, z minus 3 root 11 over 4 equal to 0. There's a tangent plane. Equation of the tangent plane. And yes, you can go and simplify this if you want, but no one cares. There we go. Done. you can multiply 1/2 and 1/8 and this one in, and then, you know, get that equal to a number and so on. So sure. So this is the way to find the tangent plane to any surface that it's given to you. And there is a shorter version that we're going to cover now, and then we're done with this half. So you find partial derivatives, and then you compute those partial derivatives at the point that's given to you. Plug in your partial derivatives, plug in your point P0, and you are done. That's technically all it is. Now, this was the explicit form, but we can also have surfaces. So this is going to be for surfaces given by z equals f of xy, because we can have that as well. Remember that z equals f of xy is a function. It's like an umbrella. Any vertical line parallel to z cutting through umbrella will cut through umbrella only once. So the shape of umbrella, which we call elliptical paraboloid, is actually a function, where ellipsoid, and that was on the same list, one above the other, in 12.1, ellipsoid is not a function. So we have to have methods to deal with both of these, right? So for surfaces given by z equals f of xy, the tangent plane is going to be given by z equals fx computed at a, b, times x minus a, plus fy computed at a, b, times y minus b, plus f of a, b at the end. So this is the formula that we get if we are using the surface over here. So now what are we doing with this? Well, if you have some kind of a surface, say you can make up anything you want, z equals 3xy to the fourth minus x squared. It doesn't matter what. You can put trig, you can put whatever you put, whatever. At the point, let's say 2, 0, because we can. 2, 0 is in the domain. When you are picking the point, make sure you pick the points that are in the domain. So what do I need? I need fx, which is partial derivative in respect to x. That's 3y to the 4 minus x squared. And I need fy. Fy would be 12xy cubed.
Yeah, actually minus 2.
Yes, I was just checking if you guys are paying attention. Very good. No, very good. I was just testing you. That was great. That was great. Thank you. It's important. So we have our partial derivatives done, and now we compute those partial derivatives at our point 2, 0. So the first one is negative 4, and fy computed at 2, 0 is 0. And all I need to do now is to plug this in. So z is equal to fx at ab is negative 4 times x minus a, so x minus 2, and then we have plus 0 y minus 0. So we have, and then we have plus f computed at 0, which would be, so I need to compute f at 2, 0. So when I plug in 2 for x, plug in 0, that dies, so negative 4 as well. so -4. So the whole thing is z equals -4x plus 8 minus 4. So the tangent plane is z equals -4x plus 4. That's the tangent plane. So now this tangent plane will give rise to linear approximation, and then we also need to cover differentials. And we'll do that next class. So let's do the lab. Bye.